Okay, well, yeah, last talk of this session before coffee. And so it's Julian, and you're on the East Coast. Thanks for waking up early to speak to us.
No, no problem. No problem. Yeah, very much thank you for having me here. Yeah, I guess I'll get started then. Righto, I am Julian Kemmerer, here talking to you today about PipelineC, talking about easier hardware description between RTL and HLS. And again, thank you to HAFDAL for having me here and supporting the remote presentation. Trying to be quick here, probably about 30 seconds to a minute per slide, so let's get going. Context and semantics to kind of zero in on what's going on here. We are writing something that looks like C, and you're getting hardware description out the other side. So natively VHDL, but you can get a Verilog conversion into there too. And right, this is between register transfer level and high level synthesis. So what are we talking about? Starting from something that traditional hardware description languages know, functions and combinatorial logic kind of go together. So PipelineC combines these, the concept of functions and modules. So on the left here, you write a function. It takes an input called input name, and it has an output. And then on the other side here is the VHDL beginning. It's a module with input and output ports. Continuing along here with these semantics here. So function invocation, you might say, is actually making multiple instances of a function or a module in this case. So on this top one here, you have a function with two inputs, x and y. They both go through a foo function. And in this case, that's two parallel instances of the foo module. And then it's followed up by a bar there. So what we're getting at here is that it's the data flow through the C function that's giving you this graph here. On the bottom here, as in hardware description languages, functions are unrolled. So this 3-iteration loop, it's passing its input, the output, input again a few times, gets unrolled. So you get 3 instances of the foo module. That's like the bare minimum syntax you might need to know to understand what's going on. But now getting into some PipelineC specific things. So you go about writing these functions, and software people are writing these functions probably because it looks like C. And you want to be able to give some kind of feedback based on, what kind of hardware does this function actually synthesize to. So PipelineC works with a bunch of tools in the back end to say, synthesize my function and tell me how many nanoseconds of delay does the combinatorial logic that I've described actually take. And so that's good for just giving folks, a sense of, I wrote a division operator and now, hundreds and hundreds of nanoseconds of delay. Don't use division kind of things. But it's this back-end specific, device-specific timing information that kind of gives PipelineC its namesake here, where it can auto-pipeline combinatorial logic for you. So you tell the tool, I'm using this Lovato FPGA part here, and I want it to run at 100 megahertz. And so the tool, knowing what these are composed of, for instance, we're a floating point here, an add's going to take longer than a multiply. It knows this internally, the delays of those operators and what those operators are composed of. And so it'll break it apart into stages for you. Final note here, these are all initialization interval of 1 pipelines. So it's not full high-level synthesis where they'll take this function and derive a state machine or something for you. This is simpler, you could say, and it's just doing pipelining. All right, so we've been talking about functions, and they've been pure functions so far, but you can also have impure functions with state, and the way that works out is with static local variables. And again, recall these, each invocation of a function actually is making a new instance. So when you call a my counter, you get a new instance, you get a new counter. And yeah, if we start looking at how these registers are actually used, on the left here, we have the value that's in the register. We take it, we do some addition on it, and then that's what's going out the return output port here. But you can mix it up here. So similar structure, but now we've taken the value right from the register, and we're not incrementing that. We are going to increment the value that is in the register, and instead what's going out the output port is just the register value without the increment. So in this case, you could get output registers, input registers, depending on how you kind of organize this. And the final bit down here at the bottom is that this is clock by clock. You can picture these functions executing over and over again, each taking one clock cycle to do. And so the tool's not going to be auto pipelining things in here for you. You've specified I have a register. This is what's going to happen each clock. You need to be able to determine clock by clock what's going on. All right, so getting some more real world examples here. This is a finite impulse response filter. Fun for any DSP folks in the audience, but generally what's going on is a sliding window. So each time this function is called, you're getting a new sample. We're going to store it in an array. And then again, each time this function is called, we're taking what's in the array. We're going to multiply all those values by a coefficient and then sum them all up. And that's your classic finite impulse response filter. As I mentioned in the last slide, using these static local variables and writing it like so, you're describing per clock what happens. The tool is not going to come in here and stretch this over multiple clock cycles because you're describing, you might say RTL style, clock by clock. That is opposed to pipeline style, you might say, where what we've done here is we've isolated the impure stateful part of things and the pure stateless mathy part of things to implement the same functionality. And now the tool, not seeing a specific relation of clock by clock description here, is free to extend the multiplies and adds, in this case, from your filter over multiple cycles to meet timing. And so functionally what that means is, you can grow your filters and not have to worry about re-pipelining them as you add more taps. A final bit of PipelineC features here before I get into actual hardware examples is global variables. So we've been talking about functions, we've been talking about inside of functions, but there is a global namespace and there are global variables, and they can be used for a lot of different things, but I'll tell you just one here today, using global variables as wires. So say you have a function like this reset guy here. It takes an input of the button, and say you could do classic debounce, synchronize the button, check for glitching, all that kind of stuff, and then you go ahead and you drive this global variable synchronous reset wire. And what that lets you do is from any other function, any other place in the hierarchy, any number of times, you can read that wire and use it to do stuff. And yeah, you don't have to go about actually wiring that down through your hierarchy to everywhere that it's used. Last little good bit there is we've specified this is in a 100 megahertz clock domain. So you try to read this wire from some other clock domain, you get an error about clock domain crossing, and go about constraining it otherwise or telling the tool to ignore it and all kinds of stuff. All right, so we've gotten through kind of the basic features, and now I want to talk about actual things implemented in hardware, some fun that came out of this. So yeah, what can you do with these combinatorial logic registers, pipelines, and wires? Well, everything. And again, thank you folks for all being here today. You're the first to hear about this fun project. My first attempt at doing DSP, and I used a software-defined radio from the company Deepwave Digital, which I have a little pulsing heart here for, because full disclosure, they are my employer. Lovely place to work, but they are not actually sponsoring this talk in any way, but they did give me access to our software-defined radio hardware and FPGA development kit, and went about writing a big pipeline function here, which does some finite impulse response filters, FM demodulation, some more filtering, and then FM de-emphasis. And I was able to listen to FM radio through my FPGA, which was a good, fun time. And all of this, earlier we saw examples of finite impulse response filters. So, I find out, I need to add a bunch of taps to my filters late in the game. Doesn't matter. The tool is just going to auto pipeline it out, and I don't need to really change any part of the design. All right, so let me make sure I got everything on here I wanted to say. Yes, I did. Okay. So, another fun example here from my colleague, Victor. We worked on this for even more than a year, but about a year or so ago, got a whole bunch of press because our ray-traced bouncing ball game, Sphere versus Shapes, got news because folks really loved how power-efficient custom hardware can be. No surprise there, but lots of fun getting that game going. I do want to spend a second telling you about how it was implemented. That radio example I just gave you before was one function, one big pipeline. This is two functions, pretty much. One function is doing the game logic, If the ball intersects the floor, it's going to bounce up. So that's the next, change its velocity. Versus on this side, it's taking things like the ball is in a certain position. For every XY position on the screen, give a pixel color. And let's see here. Of course, this, it's a big pipeline. So it's auto pipeline, hundreds of stages for that one to do the ray tracing rendering there. And otherwise, a simple state machine on the other side. And a final big actual in hardware working example here is this shared resource bus thing. So you have these pipelines. PipelineC is pipelining for you, but how do you actually use them? You're going to get data into them, out of them, and you're wanting to share these probably. And that's what I've set up here. In that these kind of cloud objects here, state machines, and completely glossed over this, but PipelineC can also do a kind of state machine style of writing things where in this code here, earlier I mentioned how combinatorial logic loops are unrolled. These are not. This actually is a state machine that's walking through states iteratively. And so each one of these clouds is a instance of that state machine, a thread, if you might say, and it's walking through and invoking, sending data into a pipeline, getting it back out, sending it into the next pipeline, getting it back out. And you can have multiple of these threads all going at once, and they're all arbitrated and shared. It's pretty complex, and I look forward to experimenting with it more, especially with, hey, what if we replaced one of these derived state machine threads with an actual RISC-V core? That would be neat. So there's some future work coming up on that. Right, and yes, I think we're on the last few slides here. Hopefully I haven't gone over time. Into future work, of course, the auto pipelining still has plenty of room for improvement. I've been mentioning timing in that, what's the delay of this combinatorial logic? But the tool actually doesn't have any concept of what's the area, what are the resources used by this logic. So it'd be great to have that kind of feedback in there and dealing with that. These pipelines are initialization interval of 1, so they're free flowing. There's no concept of stalling this pipeline or asserting feedback. The future work to look into how to do that. The finite state machines being derived. There's a whole boatload of work to be done there. That's a pretty experimental new feature. Of course, general language things like support better types and parameterize things. You want to get from C to C++, you might want to say. You might have been tempted to say, hey, can I compile all this code and just run it with a C compiler? You sometimes can, and you sometimes can get like a really fast simulation that way. It would be great to be able to do that all the time with no special setup. And just generally, I am not a compiler engineer. I don't have formal compiler training. I'm just an FPGA guy. And so really getting into an actual modern framework for doing hardware compilers would be beneficial, I'd imagine. But yeah, I think, all right, here we are at the end. Time for some questions, links to everything that's going on. And I'm happy to go back to any slides. I know I really raced through here. And again, thank you for your time, folks.
Thank you very much.
Yeah.
Can you see the room?
Well, let's see. I can't see the room, but if you want to see slides, I don't know if I can have both of you going at once. So.
Yeah, I think if you maybe stop sharing, then yeah, perfect. So these are the people you were speaking to.
Thank you, fine folks.
Yeah, questions? Yeah.
So do the FPGA tools actually reduce logic that? Like one of the interview questions I always ask our hires, I want to meet timing, and then they say, I can insert more registers, but I could also change my priority encoded multiplexer to a wide multiplexer. Do you know whether the tools do that automatically? They probably shouldn't, actually.
So yeah, I think you're getting at what's called retiming a lot, and the tools can do that. I think, for example, Xilinx Vivado has it turned on by default. But yeah, that's where I have some logic. Maybe it's a little big, so I put some registers after it, and I want the tool to spread it out across those. It can do it. I've seen it on the scale of a handful of stages. PipelineC actually just instantiates a multiplier and then registers around it. And relies on the tools for that retiming of their specific multipliers. So yeah, tools do it. PipelineC uses it to an extent. Yeah.
Yeah. And I had one other question. So have you looked at this technique called C-slowing? So you said, well, I can't introduce pipelining in my feedback loop, which is in general true, but you can make a very expensive trade-off in hardware, which is duplicate the logic
I've
in your
only
feedback loop.
Yeah, I've only glanced over some of the C slowing papers, and there's also a kind of an angle to I showed this is the code where it's not going to auto pipeline, where this is the version of the code where it will auto pipeline. Why couldn't you just have the compiler transform one version to the other? And it kind of gets into like where you're describing something clock by clock versus where you're expecting the tool to come in and maybe add some extra cycles or do some C slowing, which won't be exactly what your original, logic described, but is implementing the same thing just over a different, retimed number of cycles. So yeah, it kind of gets into, even if I could do it, would I want to? And yeah, it's still a lot of questions, but
Okay. It
good
becomes more magic.
Yeah, more magic is almost dangerous at times, but yeah, that's a great question.
Okay, we're going to have coffee here now. So thanks very much for your presentation, and we really hope that you stay for the second half of the session.
Sounds good.